Hello there, and welcome to the Science for Sleep channel. Tonight, we'll explore gravity, the force that has shaped the cosmos for nearly 14 billion years. Invisible threads pulling galaxies together across infinite space, bending light itself around massive stars, and holding your feet gently to the ground as you rest. These quiet forces have witnessed the birth of planets, the dance of moons, and the endless fall of matter through curved spacetime. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Just before we begin, if this helps you rest, consider liking and subscribing. One sleepy soul at a time. Now, let's begin with gravity. Gravity is the weakest of the four fundamental forces, yet it shapes the entire structure of the universe across billions of light years. Think about that for a moment. The electromagnetic force holding atoms together is vastly stronger, and the forces inside atomic nuclei dwarf gravity completely. Yet gravity reaches farther than any other force, connecting every star to every other star across unimaginable distances. It built the galaxies we see scattered through space like islands in an endless ocean. It gathered dust into planets and pulled planets into orbit around their suns. Gravity may be weak, but its patient accumulation over cosmic time creates everything from moons to galaxy clusters. This gentle force never stops working, never takes a break, continuously weaving the fabric of everything we can see. Gravitational waves travel at the speed of light, carrying information about cosmic collisions that happened over 1 billion years ago. These ripples in space-time itself move through the universe like waves crossing an infinite ocean. When they finally reach Earth, they stretch and compress space by less than the width of an atom, yet we can detect them. Scientists have built instruments sensitive enough to feel these whispers from the distant past. The waves tell stories of black holes that merged when our planet was young, of neutron stars that collided in galaxies far beyond our own. They travel for eons through empty space, undisturbed and unchanging, bringing news of violence that happened long before humans walked the earth. And still they come, washing over us every day, invisible messengers from the deep past. When two black holes merge, they lose mass by radiating gravitational waves, making space itself ring like a bell. Imagine two massive objects, each weighing more than our sun, spiraling together faster and faster. As they orbit, they shake space-time so violently that waves carry energy away into the cosmos. The black holes move closer with each orbit, accelerating as they fall toward their final collision. In the last fraction of a second, they spin around each other hundreds of times and then merge into one. The collision is so powerful it briefly outshines all the stars in the observable universe combined, but not with light. The energy pours out as gravitational waves, and the final black hole settles down, quivering like a struck bell until it becomes still. Mass converts directly into ripples of distorted space-time, spreading outward forever. A small fridge magnet can overcome the entire gravitational pull of Earth when it lifts a paperclip. This simple fact reveals something profound about how weak gravity truly is. The whole planet pulls down on that paper clip with all its mass, every kilogram of rock and metal in Earth's core and mantle and crust. Yet a magnet smaller than your thumb defeats all that gravitational force easily. The electromagnetic force operating in that magnet is incomparably stronger than gravity, even when gravity has the advantage of Earth's entire planetary mass. This is why atoms don't collapse under their own gravity. why you don't fall through the floor, why matter can exist in stable forms at all. Gravity accumulates its power through vast amounts of mass gathered together. On small scales, it barely whispers while other forces shout. Time moves slower in stronger gravitational fields, and astronauts on the International Space Station age slightly faster than people on Earth. This isn't science fiction or metaphor, but measured reality predicted by Einstein's theory. Clocks on the space station tick faster than identical clocks on the ground, though by only billionths of a second each day. The difference comes from being farther from Earth's center, where gravity's pull is slightly weaker. GPS satellites must account for this effect, or their navigation signals would drift out of accuracy by kilometers within days. Time itself bends and stretches near massive objects, flowing at different rates depending on how deep you sit in a gravitational well. An astronaut returning from orbit has aged microseconds more than their twin who stayed home. Gravity doesn't just curve space, but also curves time, blending them into a single fabric called spacetime. Gravity's range is theoretically infinite, meaning every atom in your body is technically pulled by every star in the observable universe. The force weakens with distance, becoming unimaginably faint across cosmic scales, but it never reaches zero. Right now, Andromeda Galaxy's trillion stars pull on you, though you'll never feel it. The supermassive black hole at the center of our Milky Way, thousands of light years away, exerts a tiny tug on every cell you have. Even galaxies, billions of light years distant, contribute their infinitesimal gravitational influence. Everything pulls on everything else, creating an interconnected web of forces spanning the entire cosmos. No object exists in gravitational isolation. We're all embedded in overlapping fields of attraction that extend forever in all directions, connecting us to structures we'll never see. Einstein's theory predicts gravity doesn't pull instantaneously, but takes time to propagate, like ripples spreading across a pond. Newton imagined gravity as instantaneous action at a distance, but Einstein showed this couldn't be true. Information cannot travel faster than light, and gravity is no exception. If the sun suddenly vanished, Earth would continue orbiting empty space for 8 minutes before the change in gravity reached us. The same 8 minutes light takes to travel from sun to Earth. Changes in gravitational fields spread outward as waves moving at light speed, carrying information about shifting masses. This means when you jump, the gravitational disturbance you create spreads outward through space at precisely the speed of light, though impossibly weak. Gravity isn't a mysterious instant force, but something that propagates, travels, moves through space-time at a finite speed. The curvature of space-time near massive objects bends the path of light itself, creating gravitational lenses that magnify distant galaxies. Light always travels in straight lines, but space-time itself can curve, and light follows those curves faithfully. When light from a distant galaxy passes near a massive galaxy cluster, the cluster's gravity warps space-time enough to bend the light's path like a lens bends light in a telescope. This allows astronomers to see galaxies that would otherwise be too far and faint to detect. Sometimes, the lensing creates multiple images of the same distant galaxy, or stretches it into luminous arcs. The massive object acts as a natural magnifying glass in space, using gravity to focus light just as glass lenses focus light through refraction. Einstein predicted this effect, and astronomers now use it routinely to study the most distant objects in the universe. At the center of Earth, you would feel weightless because gravitational forces from all directions cancel out perfectly. This seems impossible at first, but think about it carefully. Gravity pulls you toward mass, and at Earth's center, there's mass in every direction surrounding you equally. The rock above pulls up exactly as hard as the rock below pulls down. The mass to your left pulls with the same force as the mass to your right. All these forces balance precisely, leaving a net force of 0. You would float there freely, despite being at the center of an entire planet. As you move away from the center toward the surface, more mass lies behind you and less ahead, creating an imbalance that we feel as weight. But at that singular point in the middle, geometry creates perfect cancellation. 0 net gravity, surrounded by an entire world. Gravity has only one direction, as it can only attract, never repel, unlike magnetism or electric forces. Magnets have north and south poles that can push apart. Electric charges can be positive or negative, and like charges repel each other. But gravity only knows one mode of operation: attraction. Every mass pulls on every other mass, always and without exception. There's no such thing as negative mass that would push away instead of pull. This one-way nature of gravity means it accumulates without limit. Add more mass and you get more gravitational pull, period. This is why gravity, despite being the weakest force, dominates the largest structures in the universe. It adds up without cancellation, building and building as matter gathers together into planets, stars, and galaxies. The universe expands, but gravity works constantly to pull things back together. Stephen Hawking's black hole area theorem states that the surface area of a black hole can never decrease, confirmed by gravitational wave observations. This mathematical insight emerged from combining quantum mechanics with Einstein's relativity, revealing something strange about these cosmic objects. The area of a black hole's event horizon must either stay the same or grow larger over time, never shrinking. When black holes collide and merge, the final black hole's surface area exceeds the sum of the two original areas. Gravitational wave detectors confirmed this prediction by measuring the masses and spins of black holes before and after collision. The theorem connects deeply to thermodynamics and entropy, suggesting black holes aren't entirely black, but have properties similar to thermodynamic systems. Even when a black hole seems isolated and unchanging, its surface area preserves information about everything that fell into it throughout cosmic history. This simple rule about area conceals profound mysteries about information, entropy, and the nature of spacetime itself. Pressure and stress contribute to gravity just as mass does, with the early universe's radiation pressure shaping cosmic evolution. We usually think gravity comes only from mass, but Einstein's equations reveal something more subtle. Any form of energy creates gravitational effects, including pressure, tension, and stress within materials. In the first moments after the Big Bang, radiation dominated the universe's energy content, and the pressure of that radiation influenced how space-time curved. This affected how the universe expanded and how the first structures began to form. Even today, pressure inside neutron stars contributes to their gravitational fields, though the effect is small compared to mass. Deep within stars, the crushing pressure affects the gravitational field noticeably. Energy and mass are equivalent, as Einstein showed, and gravity responds to all forms of energy. The universe's evolution was shaped not just by matter clumping together, but by the pressure of radiation pushing outward in the dense early cosmos. Nothing can shield you from gravity. Unlike electricity or magnetism, there is no gravitational insulator. You can block electromagnetic fields with metal cages or magnetic fields with special materials. But gravity penetrates everything without exception. No material, no matter how dense or specially designed, can stop gravitational effects from passing through. If you hide behind a planet-sized wall of lead, the sun's gravity still reaches you exactly as before. This property makes gravity fundamentally different from other forces we know. It cannot be turned off, redirected, or blocked by any known means. Scientists have searched for negative mass or exotic matter that might repel gravitationally, but found nothing. Gravity flows through space, through matter, through everything, completely unstoppable. This is partly why detecting gravitational waves required such incredibly sensitive instruments. The waves pass through Earth as if it weren't there, barely interacting at all. The moon's gravity pulls on Earth's oceans, creating tides that move trillions of tons of water twice daily. Most people know tides relate to the moon, but the mechanism is subtle and beautiful. The moon pulls harder on the side of Earth closest to it because gravity weakens with distance. This creates a bulge of water on the near side. Surprisingly, there's also a bulge on the far side because the moon pulls the solid Earth away from the water there. These two bulges mean most coastlines experience two high tides and two low tides each day as Earth rotates beneath them. The sun also contributes to tides, though less strongly than the moon, because it's much farther away. When sun and moon align, their gravitational pulls combine to create especially high spring tides. When they're at right angles, their effects partially cancel, producing gentler neap tides. All this water movement, caused by subtle differences in gravitational pull across Earth's diameter, has shaped coastal life and navigation for billions of years. Gravitational time dilation means a clock on a mountaintop runs faster than one at sea level, though by only billionths of a second. This bizarre effect follows directly from Einstein's general relativity and has been measured countless times. The stronger the gravitational field, the slower time flows. At sea level, you're deeper in Earth's gravitational well than on a mountaintop, so your clock ticks slightly slower. The difference is incredibly tiny. A clock on Mount Everest gains perhaps a microsecond per year compared to one at sea level. Yet atomic clocks are accurate enough to measure even this minuscule effect. It's not an illusion or a problem with the clocks. Time itself genuinely flows at different rates depending on gravitational strength. Every tick, every heartbeat, every decay of a radioactive atom happens at a rate determined by the local gravitational field. You age differently depending on where you stand, though the difference is far too small to matter in daily life. Gravity accelerates all objects equally regardless of mass, so a feather and a hammer fall at the same rate in vacuum. Galileo supposedly demonstrated this by dropping objects from the Leaning Tower of Pisa, though that story might be legend. Apollo astronauts proved it definitively on the moon, where there's no air resistance. Commander David Scott dropped a hammer and a feather simultaneously, and they hit the lunar surface at exactly the same moment. This happens because gravitational acceleration doesn't depend on the object's mass. A boulder and a pebble experience different forces. The boulder feels more gravitational pull because it has more mass, but force divided by mass gives the same acceleration for both. On Earth, a feather falls slower only because air resistance affects it more than its weight. Remove the air, and gravity treats all objects identically. This equivalence between gravitational mass and inertial mass is one of nature's most mysterious and fundamental properties, underlying Einstein's entire theory of gravity. Earth's rotation creates frame dragging, where spacetime itself gets twisted and pulled along like honey stirred in a jar. This effect, predicted by Einstein's general relativity, is incredibly subtle but measurable. As Earth spins, it drags the fabric of spacetime around with it very slightly. Satellites in orbit experience tiny forces from this twisting of spacetime, causing their orbital planes to shift over time. NASA's Gravity Probe B mission measured frame dragging by watching how gyroscopes drifted when orbiting Earth. The gyroscope's axes slowly rotated even though no forces touched them directly. They were responding to the twisted geometry of spacetime itself. Near rapidly spinning black holes, frame dragging becomes extreme, creating a region where nothing can remain stationary relative to distant stars. Space itself flows like a whirlpool, carrying everything with it. Earth's frame dragging is minuscule by comparison, but it proves spacetime isn't a static stage, but something dynamic that matter can push, pull, and twist. Neutron stars have gravity so intense that dropping an object from 1 meter height would make it hit the surface at millions of kilometers per hour. These objects pack more mass than the Sun into a sphere only about 20 kilometers across, creating gravitational fields of unimaginable strength. The surface gravity exceeds Earth's by billions of times. If you could somehow stand on a neutron star and drop a ball, it would accelerate so rapidly that in a fraction of a second it would reach incredible speeds. The impact would release energy equivalent to a nuclear bomb. Even light struggles to escape the intense gravitational pull, losing energy and shifting toward redder wavelengths as it climbs out of the gravity well. Mountains on neutron stars can't rise more than a few millimeters high before gravity crushes them flat. The star's immense gravity compresses matter into exotic states where atomic nuclei merge into a sea of neutrons. These objects demonstrate what gravity can do when concentrated to extreme densities. Gravitational waves detected by LIGO stretch and compress space by less than the width of an atomic nucleus across kilometers. This measurement represents one of humanity's greatest technical achievements. Imagine trying to measure a change smaller than a proton across a distance longer than several football fields. LIGO does this using laser interferometry, bouncing light back and forth through vacuum tubes and watching for tiny changes when gravitational waves pass through. The facility must account for everything from earthquakes on the far side of Earth to trucks driving on nearby highways to quantum fluctuations in the laser light itself. When black holes collide billions of light years away, the gravitational waves that reach us are almost unimaginably faint, yet LIGO can detect them. The waves literally change the distance between LIGO's mirrors, stretching space in one direction while compressing it in another. For a brief moment, as the wave passes, your body stretches and compresses too, though by far less than the width of an atom. Space itself breathes in and out. The geodetic effect causes gyroscopes in orbit to drift over time because they're moving through curved spacetime. A gyroscope is a spinning object that normally maintains its orientation unchanged, pointing in the same direction indefinitely. But when you put a gyroscope in orbit around Earth, something strange happens. Its orientation slowly drifts relative to distant stars, even though no torques act on it. This drift comes from the curvature of spacetime itself. The gyroscope is following geodesics, the straightest possible paths through curved geometry. But what counts as straight in curved spacetime differs from flat space. The Gravity Probe B satellite carried 4 perfect gyroscopes, the roundest objects ever made, and monitored them for years to measure this drift. The experiment confirmed Einstein's predictions with remarkable precision. The gyroscopes weren't experiencing any physical force, they were revealing the shape of spacetime itself. Geometry determines motion, and motion reveals geometry. Gravity isn't a force, but the curvature of the stage on which everything moves. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. This is the essence of general relativity. John Wheeler, the physicist, summarized Einstein's theory with this elegant phrase: mass and energy don't create a force that reaches across space to pull on other objects. Instead, they reshape the geometry of spacetime itself, creating curves and warps in the four-dimensional fabric of reality. Other objects respond to this curved geometry by following the straightest paths available, which look curved to us. A planet orbits a star not because invisible strings pull it, but because the star's mass curves spacetime around it, and the planet follows that curvature. The geometry guides the matter, and the matter creates the geometry in an endless feedback loop. This represents a complete revolution in how we understand gravity. It's not a force at all, but the shape of the universe responding to the presence of mass and energy. Everything from falling apples to orbiting galaxies follows this same principle of curved geometry. If the Sun suddenly vanished, Earth would continue orbiting empty space for 8 minutes before the change in gravity reached us. This thought experiment reveals gravity's finite propagation speed. Light takes 8 minutes to travel from Sun to Earth, covering roughly 150 million kilometers. Gravitational changes travel at exactly the same speed, the speed of light itself. So if some cosmic catastrophe erased the Sun, we wouldn't know for 8 minutes. During that time, we'd still see sunlight that left before the disaster, and Earth would continue following its curved orbital path around where the Sun used to be. Only when the final photons arrived, 8 minutes after the Sun vanished, would Earth suddenly fly, off in a straight line, freed from the gravitational well. Simultaneously, the gravitational wave of the Sun's disappearance would wash over us, a massive distortion in spacetime, spreading outward at light speed. Nothing in the universe communicates instantaneously. Every influence, including gravity, takes time to propagate across cosmic distances. Gravitomagnetism is a weak effect where moving masses create gravitational fields analogous to how moving charges create magnetic fields. In electromagnetism, stationary charges create electric fields, but moving charges create magnetic fields as well. General relativity predicts something similar for gravity. A stationary mass curves spacetime in one way, but a moving mass creates additional effects resembling magnetism. These gravitomagnetic fields are incredibly weak compared to ordinary gravity, detectable only in extreme situations or with extremely precise instruments. Frame dragging, where rotating masses drag spacetime around with them, is a gravitomagnetic effect. The Gravity Probe B satellite measured gravitomagnetism around Earth, finding results that matched Einstein's predictions. Near spinning black holes, gravitomagnetic effects become powerful enough to create regions where space itself flows faster than light relative to distant observers. For everyday objects, gravitomagnetism is utterly negligible, but it reveals the deep mathematical parallels between electricity and gravity. Quantum gravity should appear at the Planck length, a distance so small it makes atomic nuclei look vast by comparison. The Planck length measures about 10⁻⁵ meters, far tinier than anything we can currently probe with experiments. At this scale, quantum fluctuations in spacetime itself should become significant, with geometry fluctuating wildly from moment to moment. Our current theories, general relativity and quantum mechanics, both break down at such scales, unable to describe what happens when gravity becomes quantum mechanical. Physicists have sought a theory of quantum gravity for decades, with approaches like string theory and loop quantum gravity offering possible solutions. At the Planck scale, spacetime might not be smooth, but foamy, with virtual black holes appearing and disappearing in quantum uncertainty. The universe's earliest moments after the Big Bang involved energies where quantum gravity mattered, so understanding it could reveal how reality itself began. For now, this realm remains theoretical, accessible only through mathematics, waiting for future experiments or insights to illuminate it. The force holding atoms together is vastly stronger than gravity, which is why you don't fall through your chair. When you sit down, electromagnetic forces between atoms in your body and atoms in the chair create resistance. The negatively charged electron clouds surrounding atoms repel each other powerfully, preventing the matter from interpenetrating. This electromagnetic repulsion is incomparably stronger than gravity's pull. If gravity were the only force, you would indeed fall through the chair, and the chair would collapse through the floor, and everything would eventually merge into a dense ball. But electromagnetism and the nuclear forces easily overwhelm gravity at small scales. Only when you gather enormous amounts of matter together does gravity's cumulative effect become dominant. A planet-sized collection of atoms has enough mass for gravity to become important. A star-sized collection lets gravity compress matter despite electromagnetic resistance. But at the scale of everyday objects, gravity barely whispers while electromagnetic forces shout. This hierarchy of force strengths shapes the universe at every level. Gravitational lensing allows astronomers to weigh galaxy clusters by measuring how much they bend background starlight. This technique transformed cosmology by making the invisible visible. When light from distant galaxies passes through or near a massive galaxy cluster, the cluster's gravity bends the light paths, distorting the images we see. Galaxies appear stretched into arcs, or multiple images of the same galaxy appear in different locations. By carefully measuring these distortions, astronomers can calculate how much mass the cluster contains, including dark matter that emits no light. Often, the cluster's gravitational lensing reveals far more mass than the visible stars and gas can account for. This provides some of the strongest evidence that dark matter exists. The technique is so sensitive it can map the distribution of dark matter in 3 dimensions, showing how it clumps and forms the scaffolding on which visible galaxies hang. Einstein's prediction that gravity bends light has become one of astronomy's most powerful tools for studying the universe's hidden architecture. Satellites must account for relativistic time dilation, or GPS systems would drift out of accuracy by kilometers each day. GPS satellites orbit about 20,000 kilometers above Earth's surface, where gravity is weaker than at ground level. According to general relativity, this means time flows faster on the satellites than for people on the ground. Meanwhile, the satellites move at high speeds, which causes time to slow down according to special relativity. Both effects must be calculated and corrected for the system to work. Without these relativistic corrections, the timing errors would accumulate rapidly, causing position calculations to drift by many kilometers within a single day. Every GPS satellite contains atomic clocks that must be adjusted to account for how space-time curves around Earth and how motion affects time. This makes GPS a practical demonstration of Einstein's theories, working in your pocket every time you navigate with your phone. Relativity isn't just abstract physics, but something engineers must account for in everyday technology. Gravity shapes galaxies into spirals, ellipses, and irregular forms through billions of years of gravitational choreography. When gas clouds collapse under their own gravity, they spin faster, conserving angular momentum. This spinning motion flattens the cloud into a disk, which can develop spiral arms through density waves rippling through the disk. Spiral galaxies like the Milky Way owe their shapes to this delicate balance between gravity pulling inward and rotation flinging matter outward. Elliptical galaxies form differently, often through collisions that scramble the orderly rotation, leaving stars moving in random directions held together by gravity alone. Irregular galaxies show disrupted shapes caused by gravitational interactions with neighboring galaxies. Every galaxy's shape tells a story written in gravitational interactions over cosmic time. Gravity orchestrates these vast collections of hundreds of billions of stars, guiding their dance through space for billions of years. The diversity of galaxy shapes reflects the many ways gravity can organize matter on the largest scales. Dark matter reveals itself only through gravity, pulling on visible matter and light without emitting radiation. Astronomers first suspected dark matter's existence when they noticed galaxies rotating too fast. Their outer regions moved so quickly they should fly apart unless some invisible mass held them together. Gravitational lensing provided more evidence, showing that galaxy clusters contained far more mass than their visible stars could account for. The universe's large-scale structure, the way galaxies cluster and form cosmic webs, requires dark matter's gravitational influence to explain. Yet despite composing about 85% of the matter in the universe, dark matter remains mysterious. It doesn't emit, absorb, or reflect light at any wavelength we've checked. It doesn't interact through electromagnetic or nuclear forces. Gravity is the only way we know it exists. Particles of dark matter presumably fill the universe, passing through ordinary matter almost completely undetected except through their gravitational effects. Understanding what dark matter actually is remains one of physics' greatest unsolved mysteries. The Earth's gravitational field varies slightly across its surface due to differences in density and elevation below ground. If you had an extremely sensitive scale, you would weigh slightly more in some locations than others, even at the same altitude. Regions with dense rock underground create stronger local gravity than regions above less dense material. Mountain ranges add mass that increases gravity nearby, while ocean trenches have less mass beneath them. Satellites orbiting Earth can measure these tiny variations, creating detailed maps of gravitational field strength worldwide. These maps help geologists understand Earth's internal structure, revealing density variations in the crust and mantle. They show where continents collided, where dense oceanic plates subduct beneath lighter continental plates, and where ancient impacts or volcanic activity created anomalies. The variations are small, less than 1% difference between the strongest and weakest locations, but they're real and measurable. Gravity might seem like a constant, but Earth's complex internal structure creates subtle changes across the planet's surface. Binary pulsars lose energy by emitting gravitational waves, spiraling closer together over millions of years. Pulsars are rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. When two pulsars orbit each other in a binary system, they create a laboratory for testing Einstein's predictions. The Hulse-Taylor binary pulsar, discovered in 1974, provided the first indirect evidence for gravitational waves. Astronomers measured the orbital period with extraordinary precision and found it decreasing by exactly the amount predicted if gravitational waves were carrying energy away. Over decades of observation, the two neutron stars have moved measurably closer together as they lose orbital energy. Eventually, billions of years from now, they'll spiral into each other and merge in a catastrophic collision. This system earned its discoverers a Nobel Prize because it demonstrated that gravitational waves exist even before we could detect them directly. The universe contains countless such systems, all slowly losing energy through gravitational radiation. Tidal forces from gravity stretch objects along one axis while compressing them along another, strongest near black holes. These forces arise because gravity weakens with distance. The side of an object, closer to a massive body, experiences stronger pull than the far side, creating a stretching force. Simultaneously, the sides perpendicular to the pull are compressed inward. Near Earth, tidal forces are gentle. They create ocean tides and slightly deform the planet's shape. But near extremely dense objects like neutron stars or black holes, tidal forces become devastating. An object falling toward a black hole would be stretched lengthwise and compressed sideways, a process physicists grimly call spaghettification. For supermassive black holes, the tidal forces at the event horizon might be survivable because the horizon is so far from the center. But for smaller black holes, you'd be torn apart long before reaching the horizon. Tidal forces remind us that gravity isn't uniform. It has gradients that pull on different parts of an object with different strengths. The equivalence principle states that gravity and acceleration are indistinguishable, Einstein's insight that revolutionized physics. Imagine being in a windowless box. If you feel weight pressing you to the floor, you cannot tell whether the box sits on Earth's surface or accelerates upward through space at 9.8 meters per second squared. Both situations feel identical. Einstein realized this equivalence isn't a coincidence, but reveals something profound about gravity's nature. What we call gravitational force might be an illusion created by curved spacetime. When you stand on Earth, you're not being pulled down by a force. You're trying to follow a straight path through curved spacetime, and the ground prevents you. From your perspective, the ground accelerates upward into you. This radical reinterpretation transformed gravity from a mysterious force into geometry. Every consequence of general relativity, time dilation, gravitational waves, black holes, flows from this single insight that gravity and acceleration are equivalent. Gravitational potential energy converts to kinetic energy as objects fall, speeding up continuously until other forces intervene. Hold a ball above the ground, and it possesses potential energy by virtue of its position in Earth's gravitational field. Release it, and that potential energy transforms into kinetic energy and the energy of motion. The ball accelerates as it falls, moving faster each moment. If there were no air resistance, it would continue accelerating until hitting the ground. This conversion between potential and kinetic energy is fundamental to understanding motion under gravity. Planets orbiting stars trade potential and kinetic energy back and forth, moving fastest when closest to the star and slowest when farthest away. Water falling from mountains to the sea powers hydroelectric plants by converting gravitational potential energy into electricity. The principle applies universally, from falling raindrops to matter spiraling into black holes. Energy takes different forms, but the total remains constant, redistributing between potential and kinetic as gravity does its patient work. Zero-gravity environments on space stations are actually freefall, where astronauts and station continuously fall together around Earth. This surprises many people who assume the space station escapes Earth's gravity. In fact, at the station's altitude, Earth's gravitational pull is only slightly weaker than at the surface. The station and everything inside it fall toward Earth continuously, but they also move sideways fast enough that they keep missing the planet. This is what orbit means: perpetual falling with enough sideways velocity to fall around rather than into Earth. Because everything falls together at the same rate, astronauts experience weightlessness. They're in free fall, just like someone jumping off a diving board, except their free fall never ends. The sensation of weight disappears because there's no surface pushing back against gravity's pull. This creates the floating, zero-gravity environment we see in videos from space. True zero gravity would require being infinitely far from all masses, but orbital freefall creates an excellent approximation. Gravity assists allow spacecraft to gain speed by borrowing momentum from planets, using curved spacetime as a slingshot. When a spacecraft approaches a planet from behind in its orbit, the planet's gravity pulls the spacecraft forward, accelerating it. From the planet's reference frame, the spacecraft enters and exits with the same speed. But in the Sun's reference frame, the spacecraft steals a tiny bit of the planet's orbital momentum, emerging faster than it entered. The planet loses an infinitesimal amount of orbital energy, undetectable given its huge mass, while the spacecraft gains significant velocity. This technique, called a gravity assists or gravitational slingshot, allows missions to reach distant planets using far less fuel. The Voyager probes used Jupiter and Saturn to fling themselves toward the outer solar system and eventually into interstellar space. Complex trajectories bounce spacecraft between multiple planets, each encounter adding velocity. The spacecraft follows curved paths through the warped spacetime near planets, converting gravitational potential energy and borrowed momentum into velocity changes that would otherwise require enormous amounts of fuel. The more massive a star, the more it curves surrounding spacetime, creating deeper gravitational wells. A star's mass determines how severely it warps the geometry around it. Our Sun creates a modest gravitational well, significant enough to hold 8 planets in orbit, but relatively shallow compared to more massive objects. A star 10 times the Sun's mass curves spacetime more dramatically, creating stronger gravitational effects. The curvature affects everything from how tightly planets orbit to how much light bends passing nearby. Extremely massive stars create gravitational fields so intense that when they exhaust their fuel and collapse, spacetime curvature becomes infinite, forming black holes. You can visualize spacetime curvature like a rubber sheet with masses creating dimples. Heavier objects create deeper dimples. Objects moving near massive stars feel these curves as gravitational attraction, but they are actually following the contours of warped geometry. The diversity of gravitational environments across the universe reflects the wide range of masses that stars and other objects can possess. Light climbing out of a gravitational well loses energy and shifts toward redder wavelengths, called gravitational redshift. Photons must work against gravity to escape from massive objects, expending energy in the process. But light cannot slow down. It always travels at exactly the speed of light, so instead of slowing, light loses energy by reducing its frequency, which means its wavelength increases and it shifts toward the red end of the spectrum. This effect is tiny for light leaving Earth, but becomes significant near dense objects. Light escaping from white dwarf stars shows measurable redshift. Near neutron stars, the effect becomes dramatic. At a black hole's event horizon, gravitational redshift becomes infinite. Light loses all its energy trying to escape and never makes it out. Astronomers can measure gravitational redshift to determine how strong a gravitational field is at a light source. The effect provides another test of general relativity and reveals information about distant massive objects by examining the spectrum of light they emit. Black holes form when matter collapses so densely that space-time curvature becomes infinite at a single point. Stars support themselves against gravitational collapse through internal pressure from nuclear fusion. When massive stars exhaust their fuel, nothing can prevent gravity from winning. The star's core collapses catastrophically, and if enough mass remains after the supernova explosion, it continues collapsing past the neutron star stage. No known force can stop it. The matter compresses to infinite density at a point called a singularity, where our physics equations break down. Around this singularity forms an event horizon, the boundary beyond which escape becomes impossible. Black holes represent gravity's ultimate triumph over all other forces. They're not objects in the traditional sense, but regions where space-time curves so severely it folds in on itself. Everything that crosses the event horizon, matter, light, information, falls inexorably toward the singularity. The black hole grows by consuming whatever comes too close, its event horizon expanding with each addition of mass. Event horizons mark the boundary where gravity becomes so strong that not even light can escape outward. This boundary defines the black hole more than the singularity at its center, which remains hidden from outside view. At the event horizon, space-time curvature becomes so extreme that all paths lead inward toward the singularity. Even light, traveling at maximum speed, cannot move away from the center. From outside, the horizon appears as a dark sphere, though not a physical surface you could pass through without hitting anything. But crossing it is a one-way journey. Once inside, every direction you could travel, every path through space-time leads to the singularity. The horizon's size depends on the black hole's mass, determined by the Schwarzschild radius. For a black hole the mass of our Sun, the event horizon would be only 3 kilometers across. For supermassive black holes billions of times more massive, the horizon can be larger than our solar system. The horizon represents the point of no return, where gravity's victory becomes absolute and irreversible. Orbital motion is continuous freefall, where an object's sideways velocity keeps it from hitting what it's falling toward. This concept surprises many people when they first encounter it. The moon falls toward Earth every moment, pulled by gravity, but it also moves sideways very fast, and these two motions combine into a curved path that circles Earth endlessly. Think of throwing a ball horizontally. It curves downward and hits the ground some distance away. Throw it faster and it travels farther before landing. Throw it impossibly fast, about 28,000 kilometers per hour at Earth's surface, and it would curve around the entire planet never hitting the ground, the curvature of its fall would match the curvature of Earth's surface. This is orbit, nothing more than falling continuously while moving sideways fast enough that you keep missing what you are falling toward. Every satellite, every moon, every planet in orbit is in perpetual free fall, falling and missing over and over, potentially forever. The strength of gravity decreases with the square of distance, so doubling the distance reduces gravity to 1/4. This inverse square law governs how gravity diminishes across space. If you move twice as far from Earth's center, the gravitational force becomes 4 times weaker. Move 3 times as far, and it drops to 1/9. Move 10 times as far, and gravity becomes 1/100th as strong. This rapid decrease with distance explains why astronauts in low orbit still experience most of Earth's gravity. They're only slightly farther from Earth's center than we are on the surface. It also explains why the Sun's gravity, despite the Sun's enormous mass, allows planets to orbit at comfortable distances. The mathematical pattern holds throughout the universe. Get close to a massive object and gravity intensifies rapidly. Move away and it weakens quickly, though never disappearing completely. This relationship between force and distance shapes the architecture of solar systems, galaxies, and the entire cosmic web. Massive objects in the early universe created gravitational potential wells where matter gathered to form the first structures. Shortly after the Big Bang, the universe was remarkably uniform, but tiny density variations existed. Regions with slightly more matter had slightly stronger gravity. This extra gravity attracted nearby matter, increasing the density difference. The denser regions grew denser still, their gravity strengthening, pulling in more matter in a runaway process. These gravitational potential wells acted like cosmic seeds, gathering hydrogen and helium gas over millions of years. Eventually, the gas became dense enough to form the first stars, then the first galaxies. Dark matter played a crucial role, creating gravitational scaffolding that visible matter collected upon. Without gravity's patient amplification of tiny initial differences, the universe would have remained nearly uniform forever. No stars, no galaxies, no planets, no life. Gravity transformed microscopic quantum fluctuations in the early universe into the rich cosmic tapestry we see today. Gravitational binding energy holds star systems and galaxies together against the expansion of space itself. The universe expands, carrying distant galaxies away from each other as space itself stretches. Yet gravity-bound structures resist this expansion. Our solar system isn't expanding because the sun's gravity binds the planets tightly. The Milky Way galaxy doesn't expand because the combined gravity of hundreds of billions of stars holds the structure together. Even our local group of galaxies, including Andromeda and dozens of smaller galaxies, remains gravitationally bound despite cosmic expansion. The binding energy represents how much energy would be required to tear these structures apart, dispersing their components into the expanding void. It's a competition between gravity pulling inward and expansion carrying things outward. On small scales, gravity wins decisively. On the largest scales, expansion dominates, carrying galaxy clusters away from each other at increasing speeds. The boundary between these regimes determines the structure we see in the universe today. Newton's apple didn't just fall, the Earth also moved upward to meet it, though by an imperceptibly small amount. Newton's third law states that every action has an equal and opposite reaction. The Earth pulls on the apple with gravity, so the apple must pull on Earth with equal force. When the apple falls, it accelerates toward Earth. But Earth also accelerates toward the apple. The force is the same, but Earth's mass is so enormous that its acceleration is infinitesimal. The apple accelerates at 9.8 meters per second squared, while Earth accelerates upward at roughly 1 trillion times less. Both objects move toward their common center of mass, which sits essentially at Earth's center because Earth is so much more massive. This mutual attraction applies everywhere. When you jump, Earth moves to meet you, though by an amount far too small to measure. The symmetry is exact. Every gravitational interaction is mutual, with both objects pulling on each other equally, their accelerations differing only because of their different masses. Gravitational waves carry energy away from their sources, causing orbiting objects to gradually spiral inward. When massive objects orbit each other, they accelerate constantly as they follow curved paths. Accelerating masses radiate gravitational waves, ripples in spacetime, that propagate outward at light speed. These waves carry energy, and that energy must come from somewhere. It comes from the orbital motion itself. As gravitational waves carry energy away, the orbit loses energy and shrinks. The objects spiral closer together, orbit faster, radiate stronger waves, and spiral inward even faster in an accelerating process. For typical binary stars, this happens so slowly it's barely measurable over human timescales. But for compact objects like neutron stars or black holes orbiting close together, the effect becomes dramatic. In their final moments before merging, they radiate gravitational wave energy at astronomical rates, briefly outshining the entire observable universe. The spiral reaches its conclusion when the objects collide and merge, producing a final burst of waves as the remnant settles into its new configuration. The Moon is slowly drifting away from Earth at about 3.8 centimeters per year due to tidal interactions transferring angular momentum. The Moon raises tidal bulges in Earth's oceans, and Earth's rotation carries these bulges slightly ahead of the Moon. The bulge's gravity pulls the Moon forward in its orbit, giving it energy and causing it to spiral slowly outward. Simultaneously, the Moon's gravity pulls back on the bulges, creating a drag that slows Earth's rotation. Over millions of years, this exchange transfers rotational energy from Earth to the Moon's orbital motion. Days gradually lengthen as Earth's rotation slows. Billions of years ago, a day lasted only about 6 hours. The Moon moves farther away, taking longer to orbit. Fossil corals preserve daily and monthly growth rings that reveal this ancient history. Eventually, billions of years from now, Earth's rotation will slow to match the Moon's orbit, with both locked facing each other permanently. But the Sun will likely end its main sequence lifetime before this happens, disrupting the entire system. Every mass in the universe creates a gravitational field that extends outward in all directions through spacetime. You create a gravitational field. So does every atom in your body, every object around you, every star and planet and galaxy. These fields overlap and combine, creating a complex tapestry of gravitational influences throughout the universe. An object's gravitational field represents how it curves space-time around it. The field extends infinitely, though becoming weaker with distance according to the inverse square law. Fields from multiple objects add together. When you stand on Earth, you feel Earth's gravity most strongly, but the Sun, Moon, and every distant star contributes infinitesimally to the total field at your location. Understanding gravity as fields rather than forces provides insight into how it works. Objects don't reach across space to pull on each other. Each object modifies space-time around it, and other objects respond to the local geometry they encounter. The field is the medium through which gravitational influence propagates. Gravity causes planets to be roughly spherical because that shape minimizes gravitational potential energy. When a large body forms from colliding rocks and dust, gravity pulls all the material toward the center. Material falls inward from all directions equally, creating a tendency towards spherical symmetry. A sphere is the shape where every point on the surface is equidistant from the center, minimizing the average distance material must fall. Any irregularity, a mountain too high or a valley too deep, creates extra gravitational potential energy. Over time, gravity works to eliminate these irregularities, flowing material from high places to low places until the surface evens out. For small objects like asteroids, internal strength can resist gravity's shaping, allowing irregular forms. But above a certain mass, gravity overwhelms material strength. Rocky bodies larger than about 600 kilometers in diameter become spherical. Icy bodies become spherical at smaller sizes because ice is weaker. Rotation modifies this, creating equatorial bulges on spinning planets. But the basic sphere emerges from gravity's democratic pull in all directions. Lagrange points are positions where the gravitational pulls of two large bodies create stable equilibrium zones. The Sun-Earth system has 5 such points, where gravitational forces and orbital motion balance perfectly. Objects placed there can remain stationary relative to both Earth and Sun with minimal energy expenditure. The L1 point sits between Earth and Sun, where their gravitational pulls balance. Solar observation satellites park there to maintain constant view of the Sun. The L2 point lies beyond Earth from the Sun, where spacecraft can orbit while remaining fixed relative to Earth. The James Webb Space Telescope resides at L2. The L4 and L5 points form equilateral triangles with Earth and Sun, and objects there are actually stable. Material can accumulate naturally. The L3 point sits on the opposite side of the Sun from Earth. These positions result from the interplay between two gravitational fields and orbital motion. Similar Lagrange points exist for Earth-Moon and other two-body systems, creating cosmic parking spots where gravity and motion achieve perfect balance. The fabric of spacetime can be visualized as a flexible sheet warped by the presence of mass and energy. This common analogy helps our minds grasp what Einstein discovered. Imagine a stretched rubber sheet representing spacetime. Place a heavy ball on it, and the sheet dimples around the ball's weight. Smaller objects placed nearby will roll toward the depression, not because the ball pulls them, but because the sheet's shape guides their motion. This captures the essence of general relativity. Mass and energy curve the geometry of spacetime, and objects follow those curves. The analogy has limitations because the real spacetime is four-dimensional, not two, and objects move through time as well as space. But it conveys the revolutionary idea that gravity isn't a force reaching across emptiness, but the shape of reality itself responding to mass. Everything from planets orbiting stars to light bending near galaxies follows from this geometric picture. Spacetime tells matter how to move, and matter tells spacetime how to curve. Gravitational waves from colliding black holes produce power output briefly exceeding all stars in the observable universe combined. When two massive black holes spiral together in their final moments, the energy release becomes almost incomprehensible. In a fraction of a second, they radiate more power in gravitational waves than all the light from all the stars in the visible universe added together. This isn't a long process. It happens faster than a human heartbeat. The black holes orbit each other hundreds of times per second in their final dance, shaking spacetime violently. The collision converts several solar masses worth of energy directly into gravitational waves that spread outward at light speed. By the time these waves reach Earth billions of years later, they've weakened to almost nothing, stretching space by less than an atomic nucleus across kilometers. Yet even this faint echo preserves information about the most violent events in cosmic history. The universe's most energetic moments announce themselves through ripples in the fabric of reality itself. Tidal locking occurs when gravitational forces cause a moon to always show the same face to its planet. Our moon demonstrates this phenomenon. We always see the same side from Earth. The moon rotates once on its axis in exactly the same time it takes to orbit Earth once, keeping one hemisphere permanently facing us. This isn't coincidence, but the result of tidal forces acting over billions of years. Early in its history, the moon rotated faster, but Earth's gravity pulled harder on the near side than the far side, creating a tidal bulge. As the moon rotated, this bulge tried to face away from Earth, but Earth's gravity pulled it back, creating friction that gradually slowed the rotation. Eventually, the rotation period matched the orbital period perfectly, eliminating the friction. Many moons in the solar system are tidally locked to their planets. Even planets can become tidally locked to their stars if they orbit close enough. The process demonstrates gravity's subtle, long-term influence, sculpting orbital relationships over geological time until systems reach stable configurations. Mass warps time, as well as space, with clocks running at different rates depending on gravitational strength nearby. This might be general relativity's strangest prediction. Time isn't absolute and universal, but depends on the gravitational environment. Strong gravity slows time relative to weak gravity. A clock on the ground runs slower than an identical clock on a tall tower because ground level sits deeper in Earth's gravitational well. The difference is tiny for everyday situations but becomes dramatic near extremely dense objects. Time near a neutron star flows noticeably slower than time far away. Near a black hole's event horizon, time dilation becomes infinite. From an outside observer's perspective, anything falling toward a black hole appears to freeze at the horizon, taking forever to cross it. But for the falling object, time proceeds normally. They cross the horizon quickly from their own perspective. This relativity of time follows directly from spacetime being a unified fabric where space and time intertwine inseparably. The inverse square law means gravity weakens quickly with distance, but never completely disappears. Double your distance from a mass, and gravity drops to 1/4 strength. Triple the distance, and it becomes 1/9. The relationship follows a precise mathematical pattern. Gravitational force equals the product of two masses divided by the square of the distance between them, multiplied by the gravitational constant. This law, discovered by Newton and incorporated into Einstein's geometric picture, governs gravitational interactions throughout the universe. It explains why planets farther from the Sun orbit more slowly. They feel weaker gravitational acceleration. It explains why the Moon affects ocean tides more than the Sun. Despite the Sun's vastly greater mass, the Moon's proximity matters more. The inverse square pattern emerges naturally from gravity spreading through three-dimensional space. As you move farther from a source, the gravitational influence spreads over an ever larger sphere, diluting with the sphere's surface area, which grows as the square of radius. Gravitational collapse can compress matter until electron degeneracy pressure or neutron degeneracy pressure, resists further squeezing. When stars exhaust their fuel, gravity no longer has fusion pressure to fight against. The core collapses, compressing matter to extraordinary densities. For stars like the Sun, collapse stops when electrons can't be squeezed closer together without violating quantum mechanical rules, the Pauli exclusion principle. This electron degeneracy pressure supports white dwarf stars at densities where a teaspoon of matter weighs tons. For more massive stars, even electron degeneracy can't resist gravity. Electrons merge with protons to form neutrons, and the collapse continues until neutron degeneracy pressure takes over. This creates neutron stars with densities so extreme that atomic nuclei merge into a neutron fluid. A teaspoon of neutron star matter would weigh 1 billion tons. If even neutron degeneracy can't resist gravity, nothing can stop the collapse. The star becomes a black hole. These exotic states of matter exist only because quantum mechanics provides resistance that classical physics cannot. Fighting gravity's relentless compression, general relativity predicted Mercury's orbital precession that Newton's equations couldn't fully explain. Mercury's orbit isn't a perfect ellipse, but slowly rotates, with the point of closest approach to the Sun shifting gradually over time. Newtonian physics explained most of this precession through gravitational perturbations from other planets. But a tiny amount remained unexplained, 43 arc-seconds per century, a minuscule but measurable discrepancy. This puzzled astronomers for decades. Some proposed an undiscovered planet called Vulcan orbiting inside Mercury's path. When Einstein completed general relativity in 1915, he calculated how Mercury's orbit should behave in curved spacetime near the Sun. His equations predicted exactly the observed precession, including the mysterious 43 arc-seconds. This represented one of the theory's first major confirmations. Mercury orbits deep enough in the Sun's gravitational well that spacetime curvature affects its motion noticeably. The effect is small but measurable, providing evidence that gravity truly is curved geometry rather than Newtonian force. No mysterious planet needed, just Einstein's new understanding of spacetime. Spacetime tells light and matter which paths to follow through the universe's curved geometry. In Einstein's picture, objects don't experience forces that deflect them from straight paths. Instead, they follow the straightest paths available through curved geometry, paths called geodesics. On a curved surface like Earth's, the straightest path between two cities is a great circle arc, not what looks straight on a flat map. Similarly, in curved spacetime, the straightest path might appear curved from an outside perspective. Planets orbit stars, not because forces deflect them, but because they follow geodesics through the curved spacetime around the star. Light follows geodesics too, bending near massive objects not because of a force, but because spacetime curvature bends the straightest path light can take. Everything moves through spacetime following the geometry. There are no forces, no invisible strings pulling objects around, just geometry determining which paths count as straight and objects following those paths automatically. This geometric interpretation represents general relativity's most radical departure from previous physics. Falling objects appear to accelerate at 9.8 meters per second, squared at Earth's surface in standard gravity. This number appears so often it becomes familiar, but it represents something profound about Earth's mass and size. Every second an object falls, it gains 9.8 meters per second of downward velocity. After 1 second, it moves at 9.8 meters per second. After 2 seconds, 19.6 meters per second. The acceleration continues as long as the object falls. This specific value emerges from Earth's mass and radius plugged into the gravitational equations. A more massive planet would have stronger surface gravity. A larger planet might have weaker surface gravity if its mass didn't increase proportionally. The Moon's surface gravity is only about 1/6 of Earth's because it's both less massive and smaller. Jupiter's surface gravity exceeds Earth's significantly. The value, 9.8 meters per second squared, isn't arbitrary, but determined by the geometry of spacetime around a planet with Earth's mass compressed into Earth's volume. This acceleration has shaped life's evolution, engineering, and every physical experience we've ever had. Gravitational potential varies across different locations, creating subtle variations in weight measurement. Potential energy depends on position in a gravitational field. Places deeper in the field have lower potential and higher gravitational strength. This means gravity isn't perfectly uniform even across Earth's surface. You weigh slightly less at the equator than at the poles for 2 reasons. Earth's rotation reduces apparent weight through centrifugal effect, and Earth bulges at the equator, placing you farther from the center. You weigh less on a mountain than in a valley because you're farther from Earth's mass. You weigh slightly more standing over dense underground rock formations than over less dense soil or water. These variations are small, typically much less than 1%, but they're real and measurable with precise instruments. They reflect how gravitational potential energy changes with position. An object at higher altitude has more gravitational potential energy, which means it sits in a weaker part of the gravitational field. Understanding potential helps explain everything from orbital mechanics to how water flows downhill. Massive galaxy clusters act as cosmic magnifying glasses through gravitational lensing effects. When light from extremely distant galaxies passes through or near a massive cluster of galaxies, the cluster's immense gravitational field bends and focuses the light like a lens. This allows astronomers to see objects that would otherwise be far too faint and distant to detect. Some of the most distant galaxies ever observed appear stretched into luminous arcs wrapped around foreground clusters. Others appear as multiple images, the same background galaxy visible in several places as light takes different paths around the lensing cluster. The technique reveals not just visible galaxies, but also the dark matter distribution within the cluster, since dark matter contributes to the total gravitational lensing strength. Hubble Space Telescope images showcase spectacular examples of this phenomenon, with background galaxies distorted into rings and arcs around massive clusters. Nature provides these cosmic telescopes free of charge, using gravity itself to magnify the universe's most distant reaches. Without gravitational lensing, much of our knowledge about the early universe would remain hidden. The geometry of spacetime becomes hyperbolic near massive compact objects like neutron stars. Different types of curvature exist in geometry: flat like a table, spherical like a ball, or hyperbolic like a saddle. Near extremely dense objects, space-time curvature deviates dramatically from flat. The specific type of curvature depends on the mass distribution and whether you're inside or outside the object. Near neutron stars, space-time exhibits extreme warping that affects everything from light paths to time flow. Geodesics, the straightest paths through curved geometry, spiral and bend in complex ways. An astronaut orbiting close to a neutron star would experience bizarre effects. Tidal forces would stretch them mercilessly. Time would flow much slower for them than for distant observers. Light paths would curve sharply, potentially showing them distorted views of stars behind the neutron star. The mathematics describing this curvature involves tensors and differential equations of great complexity, but the physical meaning remains clear. Space-time's shape determines how everything moves, and near neutron stars, that shape becomes extremely warped. Gravitational attraction between gas clouds initiated star formation throughout cosmic history. In the early universe, after atoms formed and radiation cleared, vast clouds of hydrogen and helium filled space. These clouds had slight density variations, some regions slightly denser than others. The denser regions had slightly stronger gravity, attracting nearby gas. As more gas accumulated, gravity strengthened further, pulling in even more material. The clouds collapsed slowly under their own weight, taking millions of years. As they compressed, they heated up. Eventually, the cores became hot and dense enough for nuclear fusion to ignite, and stars were born. This process repeated countless times across billions of years, gradually converting diffuse gas into generations of stars. Each star manufactured heavier elements through fusion, enriching the gas for future generations. Gravity drove the entire process, patient and relentless. From tiny initial density differences, gravity amplified variations into the richly structured universe of galaxies, stars, and planets we see today. Without gravity's ability to gather matter, the universe would have remained forever dark and empty. Escape velocity depends on gravitational pull, with stronger gravity requiring faster speeds to break free. To escape Earth's gravity completely, you must reach about 11.2 kilometers per second, roughly 40,000 kilometers per hour. This isn't because anything pulls you back at that speed, but because that's the minimum speed needed, so that even as gravity slows you down, you never stop completely and fall back. Escape velocity depends on the mass creating the gravitational field and your distance from that mass's center. The Moon's escape velocity is much lower than Earth's because it's less massive. The Sun's escape velocity, measured from Earth's orbital distance, determines how fast a spacecraft must travel to leave the solar system entirely. Near black holes, escape velocity equals the speed of light at the event horizon. Inside the horizon, escape velocity exceeds light speed, which is why nothing can escape. The concept applies universally. Any gravitational system has an escape velocity that must be exceeded to leave permanently. Understanding escape velocities allows engineers to calculate fuel requirements for space missions. Earth's gravity holds the atmosphere close to the surface, preventing air molecules from drifting into space. Air molecules move randomly at high speeds due to thermal energy, constantly bouncing off each other. Without gravity, this motion would gradually disperse them into space. But Earth's gravitational field provides a confining potential well. Most molecules don't move fast enough to reach escape velocity, so they remain bound to the planet. The atmosphere thins with altitude because fewer molecules have enough energy to reach higher elevations against gravity's pull. At sea level, air pressure results from the weight of all the atmosphere above. Higher up, less atmosphere remains overhead, so pressure decreases. The balance between gravity pulling the atmosphere down and thermal motion pushing it up determines the atmosphere's structure and density profile. Smaller bodies like the Moon have weaker gravity and can't retain atmospheres. Any gases escape into space. Larger planets like Jupiter have such strong gravity they retain even light gases like hydrogen and helium. Earth's size and gravity create just the right conditions to maintain the atmosphere that makes life possible. Gravitational energy released during collapse powers star formation and heats protostars. When a gas cloud collapses under its own gravity, gravitational potential energy converts to other forms. Some becomes kinetic energy of motion. As gas falls inward, much converts to heat as the gas compresses, and collisions between particles increase in frequency and violence. This heating is crucial for star formation. As the protostar's core heats up from gravitational contraction, it eventually becomes hot enough for nuclear fusion to begin. Before fusion ignites, gravitational contraction provides all the protostar's energy, causing it to glow dimly. Young stars shine partly from this gravitational energy release. Even after fusion begins, gravitational energy plays important roles throughout a star's life. When fuel in the core depletes, gravity causes further contraction, heating the star again and igniting new fusion processes in shells. The cycle repeats multiple times for massive stars. Gravity's patient conversion of potential energy into heat drives stellar evolution from birth through various stages to final collapse. Energy flows from gravity's relentless pull. The sun's gravity keeps planets in elliptical orbits that follow Kepler's mathematical laws. Johannes Kepler discovered mathematical patterns in planetary motion centuries before Newton explained why those patterns exist. Planets orbit in ellipses with the sun at one focus. They move faster when closer to the sun and slower when farther away, sweeping out equal areas in equal times. The square of a planet's orbital period relates to the cube of its average distance from the sun. Newton showed these patterns emerge naturally from his law of gravitation. The inverse square force law produces elliptical orbits automatically. Einstein later showed these orbits result from planets following geodesics through spacetime curved by the sun's mass. Whether viewed as gravitational force or curved geometry, the result remains the same. Planets trace elegant elliptical paths, their motions governed by precise mathematical relationships. Small deviations from perfect ellipses arise from gravitational perturbations by other planets. Mercury's extra precession required Einstein's relativity to explain, but overall, Kepler's laws describe planetary motion remarkably well, all following from the sun's gravitational influence. Gravitational perturbations from Jupiter and Saturn influence the formation of the asteroid belt. Between Mars and Jupiter lies a region containing millions of rocky asteroids instead of a planet. Early in the solar system's history, planetesimals in this region might have coalesced into a planet, but Jupiter's enormous gravitational influence disrupted the process. Jupiter's gravity stirred up the asteroid belt region, increasing collision velocities. Instead of gently sticking together to build a planet, colliding asteroids shattered into fragments. Jupiter's gravitational perturbations also ejected many objects from the region entirely, preventing sufficient mass from accumulating. The remaining asteroids represent leftovers from planet formation, prevented from coalescing by Jupiter's interference. Saturn contributed additional perturbations. resonances with Jupiter's orbit. Regions where an asteroid's orbital period relates to Jupiter's by simple fractions are nearly empty because gravitational interactions at those locations become especially strong over time. The asteroid belt structure today still reflects these ancient gravitational influences. Jupiter's massive presence shaped not just its own neighborhood, but affected the entire inner solar system's evolution. Space-time curvature near Earth is gentle compared to the extreme warping near neutron stars. Earth's gravitational field curves space-time, but the curvature is quite mild. General relativistic effects exist, but require sensitive instruments to detect. Time dilation between ground and orbit amounts to microseconds. Frame dragging from Earth's rotation is measurable, but tiny. Light paths bend very slightly near Earth. For most purposes, Newton's simpler theory works perfectly well. Near neutron stars, everything changes. Space-time warps so severely that relativistic effects dominate. Time slows dramatically compared to distant locations. Light bends into tight spirals. Tidal forces become powerful enough to tear objects apart. The geometry itself becomes difficult to visualize, departing radically from flat space. The difference between Earth and neutron stars illustrates how gravitational effects scale with density. Pack more mass into less volume, and space-time curvature intensifies dramatically. Earth's mass spread over its volume creates modest curvature. A neutron star's comparable mass compressed into a city-sized sphere creates extreme curvature. Gravity's strength depends on both mass and compactness. Mass creates gravitational fields automatically without any mechanism or medium required. This differs from how forces worked in pre-Einstein physics. Electromagnetic forces were thought to require a medium called the luminiferous ether. Gravity once seemed to need some invisible substance transmitting its influence. Einstein's relativity eliminated such notions. Mass simply curves space-time by its presence, automatically and immediately in the local sense. No medium propagates the curvature. Space-time itself responds to mass. This happens according to Einstein's field equations, which relate mass-energy distribution to space-time geometry. The curvature doesn't require effort or maintenance. It exists as long as the mass exists, an intrinsic property of how mass and space-time interact. Changes in the mass distribution create ripples, gravitational waves that propagate through space-time at light speed. But the base gravitational field exists without propagation, just the shape of space-time responding to mass. This makes gravity geometric rather than a force transmitted through a medium. The concept challenged centuries of intuition, but proved correct through countless experiments and observations. Objects in orbit experience microgravity because they're continuously falling alongside their spacecraft. The term microgravity can be misleading because it suggests very weak gravity, but that's not accurate. Astronauts on the International Space Station experience about 90% of the gravitational pull we feel on Earth's surface. The weightlessness they experience comes not from absence of gravity, but from continuous freefall. The station and everything inside it fall together toward Earth at the same rate, so relative to each other, nothing appears to fall. An astronaut floating in the cabin isn't actually floating. They're falling at exactly the same rate as the cabin walls. Some residual forces remain, like tiny atmospheric drag or slight tidal effects, which is why scientists call it microgravity rather than zero gravity. This environment allows unique experiments impossible on Earth, studying how flames behave without convection, how crystals grow without sedimentation, and how the human body adapts without weight-bearing loads. The sensation of weightlessness that astronauts describe is really the sensation of perpetual falling. Gravity shapes the large-scale structure of the universe into filaments and voids across billions of light years. Looking at the distribution of galaxies through enormous volumes of space reveals an intricate cosmic web. Galaxies cluster along vast filaments stretching hundreds of millions of light years, with enormous empty voids between them. This structure arose from gravity amplifying tiny density variations in the early universe. Regions that started slightly denser attracted more matter, growing denser still, while underdense regions lost matter and became emptier. Over billions of years, this process created the pattern we observe today. Dark matter provided most of the gravitational pull that shaped this structure, with visible matter following dark matter's gravitational scaffolding. Superclusters of galaxies mark the nodes where filaments intersect. The largest structures in the universe, these cosmic filaments, demonstrate gravity working on the grandest possible scales. Everything from individual galaxies to entire superclusters moves under gravity's influence, slowly evolving as the cosmic web continues developing. The pattern resembles neural networks or soap bubbles, but it's entirely shaped by gravitational attraction acting over cosmic time. The gravitational constant determines the strength of gravitational attraction throughout the universe. This fundamental constant appears in gravitational equations, determining how much force results from given masses at given distances. Its value, approximately 6.6 11 cubic meters per kilogram per second squared, seems arbitrary, but fundamentally sets how gravity behaves everywhere. A different value would produce a radically different universe. Stronger gravity would cause matter to collapse more readily, perhaps preventing large structures from forming or causing the universe to recollapse quickly. Weaker gravity might prevent galaxies and stars from forming at all. The gravitational constant links mass, distance, and force in precise mathematical relationships. Scientists have measured it with increasing precision over centuries, though it remains one of the least accurately known fundamental constants. Measuring gravity's strength requires delicate experiments because gravity is so weak compared to other forces. The gravitational constant doesn't change with location or time as far as we know. It's truly constant, the same value throughout the observable universe. This universality allows us to understand gravitational phenomena from falling apples to colliding galaxies using the same equations. Tidal heating from gravitational friction can melt the interiors of moons orbiting giant planets. Jupiter's moon, Io, demonstrates this dramatically. It's the most volcanically active body in the solar system, despite being smaller than Earth's moon. Jupiter's powerful gravity raises tidal bulges on Io, but because Io's orbit is slightly elliptical, the bulges shift position as Io moves closer and farther from Jupiter. This constant flexing generates enormous friction inside Io, melting rock and driving volcanic eruptions. Similar tidal heating likely maintains subsurface oceans on Europa and Enceladus, moons where ice should be frozen solid at their distances from the Sun. The gravitational squeezing from their parent planets provides enough energy to keep water liquid beneath icy surfaces. Saturn's moon, Enceladus, shoots geysers of water into space from this internal heating. Tidal heating can provide more energy than sunlight in these systems, making icy moons potentially habitable despite their distance from the Sun. The process demonstrates how gravity does more than just hold objects in orbit. It can reshape their interiors, melt, frozen worlds and create dynamic geological activity where cold death would otherwise reign. Spacetime responds to mass distribution by curving in patterns described by Einstein's field equations. These equations represent Einstein's greatest achievement relating the geometry of spacetime to the presence of mass and energy. They're actually a set of 10 interrelated differential equations of tremendous mathematical complexity. Solving them for specific situations, like the spacetime around a spherical star or inside a black hole, requires advanced mathematical techniques. The equations tell us exactly how much spacetime curves in response to a given distribution of mass and energy. They predicted phenomena nobody had imagined, like gravitational waves and black holes, which seemed so bizarre that even Einstein initially doubted them. The equations also describe the universe's overall evolution, predicting the expanding cosmos that observations later confirmed. Different solutions to the field equations describe different spacetime geometries, static spheres, rotating black holes, expanding universes, gravitational waves. Each solution reveals something about how gravity shapes reality. The equations work on all scales, from quantum-sized regions to the entire observable universe, though reconciling them with quantum mechanics remains an unsolved challenge. Gravitational compression in planetary cores generates heat through the conversion of potential energy. When planets formed from colliding debris, gravitational energy released as material fell inward heated the growing worlds. Larger bodies generated more heat from this process. Earth's interior remains hot billions of years later, partly from this initial gravitational energy. As dense material sank toward the center during differentiation, more gravitational energy converted to heat. Radioactive decay contributes to Earth's internal heat, but gravitational energy played a crucial role in making our planet geologically active. For massive planets like Jupiter, gravitational compression generates substantial heat even today. Jupiter radiates more energy than it receives from the Sun because it's still slowly contracting, converting gravitational potential energy to heat. Some brown dwarfs, objects intermediate between planets and stars, shine from gravitational compression alone, never achieving the temperature needed for fusion. The connection between gravity and heat extends from planetary interiors to stellar cores, where gravitational compression creates the conditions necessary for nuclear fusion to begin. Gravity doesn't just pull objects together, it transforms potential energy into thermal energy that powers geological and astronomical processes. The pull of gravity acts on center of mass, determining how objects rotate and tumble through space. When you throw an irregularly shaped object, it tumbles in complex ways, but its center of mass follows a smooth, parabolic path. Gravity effectively acts on a single point, the center of mass, where we can consider all the object's mass concentrated. For symmetrical objects like spheres, the center of mass sits at the geometric center. For irregular objects, it might lie outside the physical body entirely. Understanding this principle explains why divers tuck into balls to spin faster, why gymnasts extend their arms to slow rotation, and why satellites use massive flywheels for attitude control. Planetary. Rings form in the plane perpendicular to the planet's spin axis because that's where the gravitational and centrifugal forces balance for orbiting particles. Binary star systems orbit around their common center of mass, which might lie inside one star if it's much more massive, or between them if their masses are similar. The concept simplifies analyzing complex gravitational situations by reducing extended bodies to point masses located at their centers of mass. Mass concentration creates gravitational gradients that vary smoothly across regions of space. Gravitational field strength changes continuously with position, creating gradients, rates of change. Near massive objects, the gradient is steep. Gravity strengthens rapidly as you approach. Far away, the gradient becomes gentler. You must move greater distances to notice gravity changing. These gradients create tidal forces, which arise because gravity's strength varies across an extended object. The side closer to a massive body experiences stronger pull than the far side, stretching the object. Gravitational gradients determine how planets orbit, how galaxies interact, and how tidal forces operate. In everyday life, the gradient is so small we don't notice it. Gravity seems constant between our heads and feet, but Earth's gravity does decrease slightly with altitude, and satellites in low orbit experience measurably stronger gravitational pull than those farther out. Understanding gravitational gradients helps predict orbital evolution, plan satellite missions, and comprehend how structures form in space. The gradient at any location depends on the distribution of mass throughout the surrounding space. Gravitational force between two objects decreases as they separate, but increases as they approach. This inverse relationship governs countless phenomena throughout the universe. Comets approaching the Sun accelerate as solar gravity strengthens. Moons in elliptical orbits speed up at closest approach and slow down at farthest distance. Binary stars spiral together as gravitational waves carry energy away, bringing them closer and intensifying their mutual gravitational attraction. The relationship creates feedback loops. Objects attracting each other move closer, strengthening the attraction, accelerating their approach. This can lead to runaway processes like gravitational collapse or orbital decay. Conversely, objects moving apart feel weakening gravity, which eventually allows them to escape if they have sufficient velocity. The precise mathematical form, force inversely proportional to distance squared, emerges naturally from gravity's geometry. Field lines spreading through three-dimensional space dilute according to surface area, which grows as distance squared. This geometric fact underlies the inverse square law that governs not just gravity, but also light intensity and other phenomena spreading through three-dimensional space. Orbital mechanics relies on gravitational mathematics to predict satellite trajectories and planetary positions. Engineers use Newton's laws and Kepler's relationships combined with powerful computers to calculate precise orbits. Launching a satellite requires accounting for Earth's rotation, atmospheric drag during ascent, and the gravitational influences of Sun and Moon. The math determines exactly when and in which direction to fire engines to achieve desired orbits. Interplanetary missions require even more complex calculations, plotting trajectories that minimize fuel consumption while taking maximum advantage of gravitational assists. Small errors compound over time, so mission planners must account for every gravitational influence, including asteroids and pressure from solar radiation. The mathematics predicted Neptune's existence before anyone saw it, based on unexplained perturbations in Uranus's orbit. Today's most precise orbital predictions incorporate general relativity, accounting for time dilation and frame dragging effects. GPS satellites require relativistic corrections to maintain accuracy. The mathematics of orbital mechanics transformed from academic exercise to practical necessity as humanity became a spacefaring species. Matter follows geodesics through curved spacetime, taking the straightest possible path in warped geometry. This principle underlies all motion in Einstein's general relativity. Objects don't experience forces that push or pull them through space. Instead, they simply move through spacetime along paths that are as straight as the geometry allows. On a flat surface, a straight line is obvious. On a curved surface like a sphere, the straightest paths are curves called great circles. The routes airplanes follow to minimize distance. In the four-dimensional curved spacetime around massive objects, geodesics become what we perceive as gravitational attraction. A planet orbits a star by following a geodesic through the curved spacetime the star creates. The planet isn't being pulled. It's traveling straight through curved geometry, and that straight path happens to circle the star. Free-falling objects follow geodesics. Only when something prevents geodesic motion, like the ground stopping your fall, do you feel forces. Standing on Earth's surface, the ground pushes up on you, preventing you from following your natural geodesic path toward Earth's center. That's why you feel weight. Gravitational effects propagate outward from moving masses, carrying information at light speed. When massive objects accelerate, they create ripples in spacetime that spread outward like waves on a pond. These gravitational waves carry information about the accelerating masses, their speeds, directions, and how they move. The waves travel at exactly the speed of light, the maximum speed at which information can propagate through the universe. This finite speed has important implications. If the sun suddenly changed position, we wouldn't know for 8 minutes the time light takes to reach Earth. Similarly, the gravitational effect of the sun's new position would reach us after 8 minutes. Changes in gravitational fields don't happen instantaneously across space, but propagate as disturbances moving at light speed. This means gravitational information from distant events took years or even billions of years to reach us. When LIGO detects gravitational waves from merging black holes, it's receiving news of collisions that happened long ago in distant galaxies. The waves carried that information across cosmic distances, arriving at Earth to tell us about ancient violence. The strength of gravity at any location depends on the total mass enclosed within that gravitational field. This principle helps understand complex gravitational situations. Inside a hollow, spherical shell of mass, you experience zero net gravitational pull from the shell. The mass in all directions cancels out perfectly. Only mass closer to the center than you are contributes to the gravitational field you experience at your location. This explains why gravity increases as you descend into Earth up to a point, then decreases as you approach the center. Near the surface, all of Earth's mass lies beneath you. Deeper down, mass above you cancels the mass below until at the center, perfect symmetry produces zero net force. The principle applies universally. The gravitational field at any point depends on how much mass sits within the imaginary sphere centered on your location. Mass outside that sphere contributes nothing to the field at your location, a remarkable fact that simplifies many gravitational calculations. Understanding this helps explain everything from planetary gravity to the behavior of dark matter halos around galaxies. Spacetime geometry adjusts continuously as matter moves and redistributes throughout the cosmos. The universe isn't a static stage, but a dynamic fabric that responds instantly in the local sense to matter's presence. As planets orbit stars, the subtle redistribution of mass creates changing patterns in spacetime curvature. When stars explode as supernovae, the sudden change in mass distribution creates gravitational waves that spread outward. Galaxies colliding and merging reshape spacetime, on enormous scales. Even walking across a room creates infinitesimal changes in the local geometry, though far too small to detect. Einstein's field equations describe precisely how spacetime geometry couples to mass and energy at every point. The geometry and the matter distribution engage in continuous dialogue. Matter curves spacetime, and that curvature guides matter's motion, which then affects the curvature, creating feedback that shapes the universe's evolution. This dynamic relationship between geometry and matter plays out across all scales, from quantum fluctuations to the expansion of the entire cosmos. Spacetime isn't background, but participant in cosmic evolution. Gravitational attraction operates across empty space without requiring physical contact between objects. This action, at a distance, troubled even Newton, who couldn't explain how gravity worked across empty space. Einstein resolved the mystery by eliminating the problem. Gravity isn't a force reaching across emptiness, but the geometry of spacetime itself. Objects don't need to touch to affect each other gravitationally because they're not actually pulling on each other through empty space. Each object curves the spacetime around it, and other objects respond to the local geometry they encounter. The curvature propagates through spacetime, extending outward from every mass. An object moving through space follows paths determined by the local spacetime geometry wherever it happens to be. No mysterious action at a distance occurs, just objects following the geometry of the spacetime they occupy. Changes in mass distribution create gravitational waves that propagate at light speed, but the baseline gravitational field exists as spacetime's shape. This geometric interpretation removes the conceptual difficulty of forces acting through vacuum. Mass distribution determines the shape and depth of gravitational potential wells across the universe. Potential wells are useful ways to visualize gravitational fields. Massive objects sit at the bottom of wells, regions where gravitational potential energy is lowest. Moving away from a massive object means climbing out of its potential well, requiring energy. Planets orbit stars by circling around the potential wells created by stellar mass. Galaxies cluster together in enormous potential wells created by dark matter halos. The depth of a potential well depends on how much mass creates it and how concentrated that mass is. Black holes create infinitely deep potential wells. You can fall arbitrarily deep without ever reaching the bottom. Escape velocity relates directly to well depth. Deeper wells require more speed to escape. Particles rolling around potential wells behave like orbiting objects. Understanding gravitational potential helps explain why matter clumps together, how galaxies form, and why the universe develops structure over time. Potential wells provide an alternative to thinking about forces, describing gravity as landscape, that matter naturally flows down into valleys rather than being pulled by forces. Falling objects convert potential energy into kinetic energy, following conservation principles. Energy cannot be created or destroyed, only transformed from one form to another. A ball held above the ground possesses gravitational potential energy by virtue of its position. Release it, and that potential energy converts steadily to kinetic energy as the ball accelerates downward. Just before impact, potential energy has become kinetic energy. The total remains constant, ignoring air resistance. This principle governs countless phenomena. Water falling over a waterfall converts elevation potential to kinetic energy that can drive turbines. Planets moving in elliptical orbits trade potential and kinetic energy back and forth, gaining kinetic energy as they fall toward their star, converting back to potential energy as they climb away. Matter falling into black holes converts gravitational potential energy so efficiently that accretion disks around black holes shine brighter than entire galaxies. Understanding energy conservation in gravitational fields allows engineers to calculate satellite trajectories, enables astronomers to determine orbital parameters, and helps physicists understand how the universe evolves. Gravitational fields extend infinitely outward from every particle of matter in existence. Each atom in your body creates a gravitational field that extends throughout the universe. The field weakens with distance, but never truly vanishes. Right now, your gravitational field extends past the moon, past the sun, past distant stars, theoretically to the edge of the observable universe. Of course, at such distances, your field is so weak it's completely unmeasurable, overwhelmed by countless, stronger influences. But mathematically, it's there. This infinite range distinguishes gravity from nuclear forces, which operate only at extremely short ranges. Electromagnetism also has infinite range, but opposite charges cancel, limiting how far electromagnetic effects extend. Gravity has no opposite charge. Mass only adds, never cancels. Every particle's gravitational field overlaps with every other particle's field, creating the complex web of gravitational influences that shapes cosmic structure. Understanding that gravitational fields extend infinitely helps explain how galaxies influence each other across millions of light years and how the universe maintains coherent, large-scale structure. The curvature of spacetime influences how light and matter propagate through cosmic distances. Light always travels at constant speed through spacetime, but the path it takes depends on spacetime's geometry. Near massive objects, spacetime curves, and light follows that curvature, causing gravitational lensing. Light from distant quasars bends around foreground galaxies on its way to Earth, sometimes creating multiple images. The light hasn't slowed or been pulled by forces. It simply followed curved geodesics through warped geometry. Matter also responds to space-time curvature. Planets follow curved orbits not because forces deflect them, but because space-time's shape near their star makes curved paths the straightest routes available. Over cosmic distances, this curvature affects how structures form and evolve. The large-scale geometry of the universe, whether it's flat, curved like a sphere, or curved like a saddle, determines whether parallel light beams eventually converge, diverge, or remain parallel. Observations suggest the universe is very nearly flat on the largest scales, though local regions curve significantly around concentrations of mass. Gravity gathers diffuse matter into concentrated structures over immense periods of time. Left alone, gas clouds don't remain diffuse forever. Even tiny density variations create gravitational differences. Denser regions pull in nearby material, becoming denser still. This process operates slowly but inexorably. Over millions of years, gas clouds collapse to form stars. Over billions of years, stars cluster into galaxies, and galaxies cluster into groups and superclusters. Dark matter provides most of the gravitational attraction that drives structure formation, creating potential wells that visible matter falls into. Without gravity's patient gathering, the universe would remain a nearly uniform sea of particles forever. Instead, gravity transforms smoothness into structure, simplicity into complexity. Every star, planet, and galaxy exists because gravity concentrated matter over cosmic time. The process continues today. Galaxies merge, matter falls into black holes, new stars form from collapsing clouds. Gravity never stops its work of gathering diffuse material into concentrated structures, building the universe's architecture, one gravitational interaction at a time.